Okay, so then last talk of today's afternoon session is by Adam on the status of QCD precision predictions for Drell-Yan processes. Anna, please.
Yes, so thank you. This project is done with this many people here. It's let me not read them aloud. So there are quite a few, and I don't really want to waste too much time. So as we already heard from Massimiliano, by the time of high Lumi LHC, we will have 2% uncertainties. But actually, right now, for example, for the Drell-Yan process, this is already available. So, for example, if you take a look at CMS data for neutral current Drell-Yan going to a muon pair, we can see that at the Z mass, we have roughly a 2% uncertainty. And for example, if we take a look at the Atlas data and considering, for example, for the electron pair production, for very low lepton pair PT, this is averages at 0.2%. So this is pretty good. Okay. And, you know, Drell-Yan is also very interesting because of many different things. So, for example, if we take a look at alpha's determination, in that case, we need, for example, at least next to leading order. If I just borrowed a couple of figures from a recent NNPDF paper, if we take a look at this bell shape at next to leading order, we can see that this is very wide. So we cannot really have a very precise alpha's determination. And if we go to next to leading order, the situation gets a bit better. So this is a pretty good reason for high accuracy Drell-Yan predictions to have. And also it is very important, not also for alpha's determination, but also for PDFs. Because, for example, if we stick this NNPDF collaboration, we can see that the collider Drell-Yan is taken into account. And if we have this prediction very precise, it can help enhance PDF determination as well. And of course, for example, it is important for WMAS measurements. Again, this is a very random paper by the LHCb collaboration, and using these kind of calculations, they were able to make a measurement for the WMAS. So these are used in many different areas. And okay, this was kind of the motivation or the introduction. Let's talk a bit about our previous work, what we did with respect to Drell-Yan with Sven and Zoli and Sergey back in the day, where we pointed out that linear power corrections can be quite large for Drell-Yan production, especially if we are in the forward region and have some symmetric cuts, right? So, for example, if we are in the central region and we have the pseudo rapidity for the lepton pair to be 0, we can see that the ratio of the radiation phase space over the Born phase space has this linear dependence on QT. And actually, this is a quite strong dependence. This is a linear dependence. This dashed line shows this arm cat value, which is used, for example, in the DyNNLO or the matrix framework to parameterize the slicing. And this is a quite huge effect, right? So these power corrections can be huge. And if we neglect them, for certain processes, the theoretical prediction cannot be that precise, right? So, for example, this is what we showed in our previous paper. We made some very high accuracy runs with fuse. These are the black lines. And we made a comparison with DrellYan analog, which is a legacy code, with matrix and MCFM. And what you can see, this deviation, a couple of % deviation from fuse, right? Fuse is a local subtraction method, so it should be considered, well, not de jure, but de facto standard, right? And we have these kind of deviations, and these deviations are the most visible in the case when we are in the forward region having symmetric cuts, as you can see from these comparisons. So they can amount to even 10%. So this was a clear indication that maybe there's some missing non-negligible linear power corrections. And actually, this was a very interesting. I thought some future studies and further studies by other groups. So, for example, the matrix group sit down and incorporated linear power corrections in their code. And from this very low panel, it shows the rapidity for the lepton pair. You can see the improvement if you include the power corrections. You can see this brown dash double dot line here. This was the original calculation. What actually I showed, let me go back. I think here, right? And if they include the linear power corrections, these are this, well, purple dashed line, the agreement becomes almost perfect, right? So these linear power corrections for this kind of process, this set of cuts really make a difference. And again, there was one more publication, one paper by a different group, and they showed these, they call it fiduciary power corrections. And surprisingly, if we go here in QCD expansion, these power corrections increase, right? So it's, for example, for a next to leading order calculation, it's not that huge if we can stick to some QT cat value, which is fairly small. But as we go further and further, deeper and deeper in the QCD expansion, the size of these corrections increase more and more. So there's more room, or there's more need to incorporate them. Okay. And also when we did this comparison and also this preliminary study about the power corrections, we had some missing pieces. So for example, we could not compare against an analog jet, and we could not compare against DY turbo. DY turbo is a re-implementation of the QT subtraction in a different framework, but an analog jet is one another local subtraction scheme. And I said that, okay, we chose fuse as the de facto standard calculation to compare against, but okay, we only said, okay, this is local subtraction, should be more or less, it should give more or less reliable results even with symmetric by comparing against some other. Those that I already implemented. There was some need to update or plot the comparison in part. And this, and again, you know, symmetric cuts are not very good. And if we have some local subtractions, maybe possibly some predictions and how these symmetric cuts alter, for example, the cross section, or what kind of tendencies we can see. Okay. So this is one of the missing pieces from our original paper. This is a comparison between fuse and an analog jet. Again, the black line is the fuse result, and the blue dashed line is the analog jet result for W plus production, W minus production, and for that production in the central region and also in the forward region. And as you can see, the agreement between the two calculations are quite remarkable. They are local subtractions, so that's one possible reason behind. And again, they are agree everywhere. So even in this very problematic region, what we saw previously. Okay, there was one more thing which was missing, and this was a comparison against DY turbo. This is preliminary because I still miss one plot here, and this is for the Z production in the forward region. But we can clearly see the comparison with fuse that, again, if we stick to the original DY turbo implementation, there's some difference. But if we include these linear power corrections, or what the original authors call fiduciary power corrections, the agreement increases, right? And it becomes more or less perfect for Z production in the central region, right? So this is a region that local subtraction calculations by default working quite nicely for example, Drell-Yan processes. For slicing methods, symmetric cuts are problematic because the final state is a bit more problematic in this code, because the soft radiation can enhance some logarithms, and this can worsen the QCD expansion. But again, this does not mean that these methods cannot be used. They can be used if we calculate some missing pieces, right? And with this, we can bring the level of agreement to a very, very nice level. Okay, so this was one thing which was missing from the original paper. And the other is a more detailed study of the symmetric cuts, right? So if we go back to the original publication by these groups here, these are by blue color. So if you hover your mouse over these texts, you can see the links and you can download the paper. I did not really bother with writing down the e-print numbers just to make it a bit more compact, right? So if we go to these papers, we can learn that actually there are large logarithms when we have some symmetric PT cuts on the decay products, and only these large logarithms are partially canceling. And actually, as it turns out, these produces some challenges for slicing methods, right? But if we include linear power corrections, it can help. And we can, as we can see from this right panel, we can make these calculations very, very nicely agree with local subtractions if these kind of power corrections are included. So this is just the Z production in the forward region with the new matrix code, which includes the linear power corrections. And as you can see from the blue line, this is pretty much close to the fuse results. So that's a good indication that if you keep your linear power corrections under control, your result, your predictions are completely in line with local subtraction prediction or with other predictions as well. Okay. But local subtractions are not a solution to the problem, right? All of these are solutions to the problem, and for all the methods you can show some observables which are tough to calculate. So, for example, on this slide I picked one observable. This is the electron charge asymmetry, and this is a notoriously hard to calculate. Observe, well, this is just a difference, right? So it's very hard to keep the numerical uncertainty low. As you can see from this figure, this black uncertainty band shows the uncertainty coming from fuse. And if you can say, oh, okay, wait a minute, what we are talking about, it's there's still a huge disagreement between matrix and fuse. Well, not really, because it's true that, for example, the matrix result tends to be a bit larger than fuse, but again, the uncertainty coming from fuse is quite huge, so we are still overlapping, right? This is a reason that this is a tough observable to calculate, okay? So sticking to symmetry cuts, what we can do? For example, we can do the following game. We can try to go to staggered cuts, right? So when we impose different cuts on the two different leptons, and we change the cutting difference between these two leptons, and we can try to make a sweep in the PT cut space and see how the cross section behaves, right? Because we have somehow some intuitive sense that, okay, if we have some staggered cuts, the calculation is much more easy to do. And if we have some symmetric cuts, we have these partially canceling lobes. So what's the transition between these two different regions or approaches? And this is what we try to take a look at the next to leading order. We impose this set of cuts on the two leptons of the final state, right? These are the theta functions, and we sweep the cut space between -5 and 5 GV and see, for example, with the help of an analog jet, what happens. Okay, so this is Z production. You can see the cutting scene here. This is the delta PT between -5 and 5 GV. This is a sweep, right? So we select a delta PT value, we calculate the cross section. For that value, we put it into the histogram, we change the cutting seam, calculate the cross section, and so on and so forth. So at leading order, what we can see? Well, if we increase this delta PT value from -5, there's this very small decrease of the cross section, but as we pass the 0 value, there's a change of slope, right? This is the traditional result, what we saw in the literature. And you can ask the question, okay, what happens if we go to next to leading order? Well, it gets more severe. The cross section starts to decrease until the point of delta PT equals to 0. Then there's this so-called cusp formation, or at least I call it a cusp formation. And the cross section starts to increase, then decrease again, right? So if you do this sweep in the cut space, you have this very, very strange behavior of the cross section. And you can ask the question, okay, what happens if we increase the perturbative order? Let's add one more order, perturbation theory. Again, the same trend happens, but this time this cusp formation shrinks quite a bit, right? So it's quite remarkable. What we have, we start to accumulate some large logarithms, right? But as we go deeper and deeper in the QCD expansions, we have more and more cancellation between these logs. And okay, you can have several ideas what can come next if we include the next to leading order, but somehow this cusp formation should vanish if we include more and more terms in the QCD expansion, right? So this is quite remarkable how the cross section changes. So these symmetric cuts are quite delicate, And I think this is a quite nice plot to really argue with this one. And okay, we can zoom into this region, and you can see that, okay, in this case, the leading order, you cannot really see this change of slope, but again, you can see this interesting cusp formation in this. Right, so this is when you have some staggered cuts and you decrease the PT difference between the cuts you impose on your leptons. And actually, yes, okay, I already summarized this. I don't really have to go through this. This is just the previous figure repeated. Yes, and after our previous study, there was a paper by Gavin and company, and they started to argue, because of the linear power corrections, that maybe we should change the cutting seam from this linear staggered cuts, what I showed here, to something else, right? They claim that, okay, don't use this kind of cuts, because this will include linear power corrections. And they claim that if we change to this product set of cuts, in that case, you can change, or you can go from linear power corrections to quadratic power corrections. So it seems that you can be a bit more your calculation can be a bit more numerically stable. So what happens if we include these cutting seams, right? This is the previous case, right? Just for comparison. This is the new case when we impose these product cuts, so to speak. Well, what happens? Again, at leading order, we have this change of slope. At next to leading order for this Z production, well, it changes a bit, well, right? We should focus on the red line. It changes a bit, but still we have the cusp formation. Maybe it's not that severe, but the characteristics is the same. The behavior still remains. And if we go to next to leading order, it starts to vanish, as in the case of the ordinary linear cutting seam, right? So this suggestion to go from linear cuts to product, oh, thank you, to product cuts, it's does not really mean a solution for this kind of process. Maybe this is a solution for example, Higgs production decaying into a photon pair or something like that. But for this, it's not really, right? But I think this is more interesting. So, for example, when we take a look at, I don't know, the right-hand side, for example, on the x-axis, you can see this sweep between -5 and 5 GeV in delta PT. And we make the ratio between the product cut scene and the linear cut scene, right? So the product cut scene, when you have the product of the PTs under the radical, and the sigma lin is the old-fashioned cut. And what you can see is that the ratio at next to leading order, it's more or less aligned. So in this region and in this region. What this means? This means that, okay, at next to leading order, we really see this tendency that this product cut seam gets rid of all the linear power corrections, right? Because we are making a product of the we are making the ratio of the product and the linear cross section, right? So the appearance of these lines here, it's a clear indication that, for example, if you have the product cut seam, there is no linear power correction, you only have quadratic power correction. But again, if we go to next to leading order, you see the emergence of logarithms, right? So this clearly shows that, okay, maybe going from the linear cutting seam at next to leading order seems to be a solution, but if we add one more order in perturbation theory, we have this reappearance of the logs, right? So you are basically, by including these product cuts, it means that you are sweeping your logarithms not under the rug, but under the next order in perturbation series, so to speak, right? And if you take a look at the ratio of the next to leading order and the next to leading order cross sections for the two different cutting seams, you cannot really see a change in the characteristic or change in the behavior. Maybe in the case of the cutter in the product cutting seam, the discuss formation is a bit less severe. Maybe the situation improves by a factor of 2 or 3, but again, the structure is still there. So there's this question whether this improvement was redoing all the experimental analysis or not. Because, for example, if this seam would completely eliminate discuss formation, the situation would be completely different. But again, it's not eliminating it. It simply puts the problem to the next QCD approximation level, so to speak. Okay, so this is just to summarize the previous plots. So again, if we use product cuts, the characteristic improved, but this improvement is only a factor of 2 or 3, so it's not that dramatic. The behavior is still there; it's not removed, and this is actually our personal opinion that the improvement is not that significant to really worth redoing all the experimental analysis again, because it can be quite tedious and it could take a lot of time and energy, which should be spent elsewhere. Right? And this actually brings me to the summary immediately. I tried to show you that several methods are available for Drell-Yan production, Drell-Yan production, which has next to leading order QCD accuracy. I showed that if we include linear part corrections, it can certainly improve the agreement of slicing methods compared to local subtraction methods. And I try to show you some comparisons and try to convince you that if we have some local subtractions, all these calculations are in agreement. And I try to show how the symmetric cuts spoil the perturbative expansions, and that product cuts are really not a solution to the problem, but maybe resummation or going to n-cube is. So with this, thank you very much, and thank you for your attention.
Thanks, Adam, for this nice presentation. Questions and comments?
I mean, I'm not sure I understand the logic behind all this. So, okay, so symmetric cuts, they are problematic. Okay, the fact that local is not that for symmetric cuts local subtraction gives the right result, because simply you are on a point on which you know that there are issues. So I mean, you get two numbers which are in agreement with an low jet and then the fuse, okay, but then I mean you can add the power corrections to the methods, to the slicing methods, you get the same result, but this doesn't solve the problem.
No.
So then you show this curve as a function of delta PT, but I mean, so one should simply use staggered cuts. What's the problem in using staggered cuts? So why should I look at what happens? Of course, at delta PT going to 0, I go on the problematic point, so I find again the problem. But if I work at delta PT non-zero, I am in a situation in which these issues are absent. So if then we can discuss whether it makes sense to redo everything or not. This is I'm not able to answer, but I would say if I should start an analysis now, I would definitely not start from the symmetric point, where I know that whatever method I use, this is a phase space region in which we know that the perturbative series has troubles. So whatever, regardless of what method we use. Would you agree with this? So I'm not sure what you are after. So what is your conclusion?
Well, the conclusion is, I think if I would like to put it very, very straight, it's, for example, the first representation of this path formation of this very small path next to leading order, because there was no study previously. So there was no scan in the cut space, in the cut parameter space, and to see.
Yeah, but still, it's clear that you are.
Yeah, you use the mic. Yes.
I mean, if you are, if you start from delta PT, which is non-zero, then you are okay. Then if you go back to delta PT equals 0, you go to the symmetric cuts again. So, you cannot find it. You find the problems that we know already. And what you have shown is that these product cuts maybe are alleviated a little bit, but still is there.
Yes, exactly. Yes, this is what we found. Yes.
And just to say, so I completely agree with the remark by Massimiliano. So if I'm not mistaken, this feature of symmetric cuts, it's similar with jet production, right?
Yes.
So, and it was known, at least for the HERA people, at least like 20 years ago, and already measurements were done.
Yes, exactly.
It's really a simple solution. Just take this delta PT, I don't know, 3 or 4 GeV and use in the future measurements. But my remark is about this product cuts on the product. I'm not sure it can be done experimentally, because if you have one lepton with large PT, say 50 GeV, then your second lepton would be with 8 GeV, and I'm not sure it can be measured. It would be just it would come with just too much of background and with extra systematic uncertainties.
Well, I'm not advocating for the product cut. So this is a pretty good
it's
pretty
another
good argument.
Just experimentally.
Yes. Thank you. Yes.
You had a question. Okay.
I have a curiosity, both for you and Massimiliano.
Yes.
Since you use matrix in part of this comparison, can you also run with the QT resummation on? Because this in principle should alleviate this problem. So maybe, just to see what is the effect of running, also turning on the QT resummation.
Yes.
So, matrix, we have hidden the QT resummation, and it has been replaced by Radish. So you can do it with Radish, or whatever resummation you do, it should sort of smooth away this behavior. Yes. In practice,
So the alternative of changing the cutting.
Actually, if I remember correctly, maybe Sven, maybe Sven knows better, but in the early Atlas analysis that they were doing, using DrellYan with of course with a finite value of the cut, they were using it, if I remember correctly, because it was giving a smoother. Of course, it's sort of using a finite cut to smooth away this cusp behavior. No, that you find it to do the calculation.
Yeah. So I think you're right. For the symmetric cuts, the solution should be that you do resummation in this delta PT, so basically QT resummation to all orders, and that should smoothen the curve, and that would be the solution to the problem for symmetric cuts. Or otherwise, you basically use staggered cuts. I mean, a shift of 1 GeV would be enough. It's, I mean, for me personally, as a comment, it's just experimental measurements were made without knowledge from Hera times and from theorist input, and now we have this data, and the question is, what do we do with it? And then, so if you go to the next slide, I think for the next one, the one where you have the K factor, I think. So yeah, right. So on the left side, you basically see you see this for symmetric cuts. You see a steep cusp. The derivative of the cross section has a divergence as a function of delta PT, and this happens on a range of a few hundred MeV. So it's a question to the experimentalists: what is the uncertainty in the PT resolution of their leptons? Because then you're talking an uncertainty of 1 or 2%, and that's significant compared to the overall experimental uncertainty budget. So this is, I think, the takeaway message from this study, that we can really map it out. We can quantify this uncertainty, and one should advise them to do something about it. Either use resummation at the point for symmetric cuts, or go to staggered cuts and shift it by GeV or 2, and then you're safe.
Yeah, that's right.
Other questions or comments? Okay, this is not the case. Then let's thank Adam again.
Okay, thanks. Yes.